Hi folks, this is Dan from FTC University Challenge Team CU Hyperloop, and I'm going to be going through the physics of launching a ring. So the first thing we're going to do, we're going to just set up kind of an example problem. So how do I use this? All right. Perfect. All right, so we've got a, let's see here. We've got ourselves on the field, and we are about 1.8 meters away from our goal here. And our goal is, we're talking about the high goal right now. We're calling it 0.9 meters high, or 36 inches. And 1.8 meters is 72 inches. So this is about 6 feet. This is about 3 feet. Now we've got a robot back here, and it's trying to launch our ring at some trajectory. And we want the top of our trajectory to be right in the middle of the goal. We don't want to be still going up when we pass through the goal, and we don't want to be coming down when we pass through the goal. This should make it the easiest for us to actually put the ring through, because it gives us the largest period of time where it's at that height. You'll notice that when it's still kind of moving at a high speed, it's kind of still going up in this upward trajectory. So if we use kind of the top of the curve, that'll be the flattest point of the trajectory. Okay, so then if we're going to talk about the physics, we should talk about the first thing we want to do is we want to cap that. We want to have our peak. We want to have our peak at 0.9 meters up. Now let's see if I can. Okay, we want to have our peak at 0.9 meters above the ground. And in order to figure out what that means, we need to figure out exactly what we want our initial velocity in the y direction to be equal to. So the reason we're able to talk about just the y direction, so just the y direction right now, versus then talking about the x direction as well, is because y and x are perpendicular to each other, which means that any sort of forces occurring in y aren't going to occur in x, and vice versa. So, for instance, the force occurring in y is the force of gravity. So gravity is pulling down on our ring. But that gravity is pulling perpendicular to the x-coordinate, so there'll be no effect on x versus y. So if we want to find out what this v naught y is, we need to set up an equation. And we're going to use a kinematic equation. So there's 4 of them. You can easily Google them and see a bunch of different resources on learning about them. So this is about, I think, junior year of high school level physics. So that's just kind of a reference point. But really, any high schooler that's taken Algebra 1 should be able to figure this stuff out. All right, so this equation is Vy squared, so Vy being your final y velocity, and V naught y being your initial y velocity, squared plus 2a delta x. And a here is going to be equal to g, the acceleration due to gravity, which is equal to 9.8 meters per second squared. Okay, so our delta x here, so we're going to be talking about initially we're shooting, and then at the end we're going to be at the top of our arc. I guess you can't see my cursor right now, maybe, but at the top of our arc. So our delta x is equal to 0.9 meters. And my apologies. Let's do delta y rather, and not mix up our coordinates. Delta y is equal to 0.9 meters. And then we're solving for this initial v velocity, and our final known that we need to kind of quantify here is our vy. So what's our final velocity in the y direction? So we're talking about the top of the arc, remember, and we're only talking about the y coordinate. So when we reach the top of our arc, that's the point where we're turning around from going up to going down. So at that point, we're moving with a y velocity of only 0 meters per second. So we're turning around, so our velocity is at 0. So what that means is we can come over here and cross out our vy squared, and we can move v naught y squared to the other side of the equation. So we can put v naught y squared, and I should also clarify this is a negative value here. V naught y squared equals 2g delta y. So if we work this out, if we plug in our numbers, we've got v naught y, and then this negative cancels with the negative that we have in our g, the 9.8, and we get equals the square root of 2 9.8 meters per second squared times 0.9 meters, all under the square root. So we've got meters times meters, so meters squared over seconds squared, and we take the square root of that, so we're left with the units of meters per second, and that's our v naught y value. So v naught y, when you actually get down to the numbers, comes out to be 4.2 meters per second. Okay, so now what are we able to do with this number? So we're able to say, okay, 4.2 meters per second, that's how hard you need to shoot it in the upwards direction. But now we also want to find out how hard do we need to shoot it in the x direction, and what's the limiting factor there. So like we said before, we've got this arc, and we've got our goal up here, and it's 0.9 meters, and it's 1.8 meters away. So if we shoot something up at 4.2 meters per second, we need to figure out how hard we need to shoot it in the horizontal direction in order to get to this point right here. So if we're shooting at 4.2 meters per second, the best way that we can correlate these two things is through time. So we're going to start talking about time, and specifically time of flight. So how long does it take for our ring to get from this point here to this point here? So one thing we can notice is that the reason we're capped here, the reason this peak is significant, has nothing to do with our x direction. It has only to do with our y direction. So what we can say there is that given some acceleration, it will take that 4.2 meters per second and put it to 0 after some time, and that is our time of flight to the peak. And in this case, we're going to want to use the equation, let's see here, we're going to want to use delta y equals 1/2 at squared to find our time. And I suppose that should actually be, oh, shoot. Come on. This should actually be delta t squared to be more precise. So the delta here and the delta above is just referring to the change in that variable. So we're talking about the y final minus the y initial, and the time final minus the time initial. So if we take this equation, or run through this already. Let's see here. Okay. So our delta y is 0.9 meters. That's how high we need to get up. And our acceleration is in the y direction, so in this direction we're talking about. So that's, again, the 9.8 meters per second squared of gravity. And our delta t is what we're solving for, so then our delta t squared. So what we're actually talking about right now, we're talking about a little bit of, we're using some physics symmetry. So the time of flight that we really are curious about is how long does it take to get from this point to this point. And if we do that, we have to talk about this initial velocity and how it turns to 0. But what we can instead do, which is a little bit easier, is think about this. So the time it takes to get the ring from this point to this point is actually equal to get from the peak back down to the same level as the start. So if we talk about this scenario instead, it's more simple because our initial velocity is set equal to 0. We have to use a kind of a more complex equation if we're going to talk about this scenario. So we can ignore that and just take for granted that we've got this symmetry that going from the bottom to the top is equal to the top to the bottom. So when we actually evaluate this, we get that the delta t to get from the bottom to the top, or from the top to the bottom, is 1.0 let's see here, no, 0.43 seconds. 0.43 seconds. So great, we now have the amount of time it takes to get to the peak, and we also have our initial y velocity. Excellent. So now let's find out what our initial x velocity needs to be. So if we talk about our x coordinate, we can once again just mention really briefly, we've got this decoupling because we are at a perpendicular between our coordinate systems. So forces occurring in y do not have any sort of effect in x because they're at perpendiculars to each other. Which means that when we launch this ring, basically all we need to think about is the force of gravity. Air resistance is quite negligible here because we're dealing at low speeds with a relatively streamlined object, being the disk on a side view. So the velocity in the x direction is actually constant. And you might need to think about this for a minute, but basically if you shoot a ball, it will kind of go in this arc, and it will start off fast and then slow down when it gets to the top and then speed up again. And we all kind of know that from just tossing a ball straight up and down. But if you start watching the x coordinate, you'll notice that the actual time it takes to traverse any horizontal position is identical for the flight, which means that we can use the simple equation v equals distance over time, or velocity or speed equals the distance traveled over time, because we're saying that we're taking up more distance in the exact same amount of time for every point we are along this arc when we're in that x direction. So the other way to put that is that our horizontal velocity is equal to our initial horizontal velocity, which is equal to the distance it travels over time. So in this case, it is 1.8 meters traveled over 0.43 seconds. So 1.8 meters divided by our 0.43 seconds. And that is equal to 4.2 meters per second. Awesome. So our Vx V naught x initial is 4.2 meters per second. Our y naught is equal to 4.2 meters per second. Our time of flight is equal to 0.43 seconds to get 3 seconds to get to the peak. And now we're able to kind of work a couple of things out. So you'll notice that these two numbers are at the same speed. So what that's telling us is that we're going to be launching at a 45-degree angle because our velocity is equal in the x and y directions. So you can work this out, but that means we're setting up this triangle, a 1 by 1 by square root of 2 triangle. That's what happens when you've got a right triangle with a 45-degree angle. So now if we want to find out what this 45-degree angle is, we can set up the Pythagorean expression to find out what our just regular old v naught is. And this is v naught the vector now instead of the components. So v naught the vector, and vector is just denoting that it's got a direction and it's got a magnitude. So we're saying it's got a direction of 45 degrees and it's got a strength or speed or magnitude of equal to the square root of vx naught squared plus vy naught squared. And this comes from, this is Pythagoras' theorem, and I'm relatively certain that every high schooler knows this, but just in case, you can look this up. So our v naught is then equal to, where did I write it down? 5.9 meters per second, if I plug things into my calculator right. So we have to shoot our ring at a velocity of 5.9 meters per second at an angle of 45 degrees. So what does that actually mean in terms of the engineering side of things? So how much energy, how much work are we doing on this ring? So if we take a ring and we say it's moving at a speed of 5.9 meters per second, there are a couple of different things we can ask. We can ask how hard we pushed the ring, and we can also ask how hard do we push the ring and over what distance. So that's called work, and we don't really need to get into that too much, but it's just force times distance, and actually it's force dotted with distance. But what that just means is that we're taking the force in the x direction, and we're taking an integral of it from a start to a finish. But if you haven't taken calculus yet, don't worry about that. Just kind of recognize that this is the concept we're talking about. And this force times the distance is actually equal to energy. And in this case, specifically kinetic energy, which just refers to the amount of energy an object has because of movement. So we've got 5.9 meters per second of velocity, and we just wrote that down for no apparent reason because we need to talk about kinetic energy first. So kinetic energy, an equation for that, Ke, sometimes called T, equals 1/2 mv squared for a simple object. And this mass here, we've got a mass that's equal to 0.03 kilograms, or about 31 grams. Apparently there might be some issues with some of the rings, so this might be plus or minus of a couple of grams. So definitely weigh your rings to figure out what's going on there. So if we evaluate this, if we take our 1/2 times our mass of 0.03 grams times our velocity squared, we get that our t, so t equals 1/2 0.03 kg times 5.9 meters per second squared. We get that our energy is equal to, our kinetic energy is equal to 0.4 or 5 joules approximately. Which means that we've got to take this ring and we've got to put around 1 joule, about a half a joule of energy into it. So to play things carefully, on the engineering side of things, let's round this limit up. So whenever we build a system, we're going to assume that we're going to lose a pretty good amount of energy to friction and heat, and just generally not perfectly translating energy into motion. So let's round this up to, let's say we need to put 1 joule of energy into our ring. So what does that mean? So the way CU Hyperloop decided to make our shooting mechanism for these rings to get into the high goal is that we built a spring system. So we've got 2 arms and they're pivoting around a center axle, and we have some springs that pull down like this, and basically when we release some clips here, that propels our ring out and up this direction. And the thing about springs is we know quite a lot about springs. They're characterized very well. And if you want to learn more about that, you can look up what's called Hooke's law. And Hooke's law says that F, force from a spring, is equal to negative kx, where x is the displacement of the spring. So a spring is some distance long, and then when you put some sort of weight on it, it'll kind of expand a little bit, and you'll get some new distance that we'll call dn. And then if you take dn minus d, that equals x in this equation. Now this negative k here, this is called the spring constant, and this is for most kind of steel spring characterizations that are just relatively constant. If you're not pulling your spring too hard, you're able to just assume this is a constant value. But anyways, this is the relationship in order to get the force a spring is producing. Another thing that you can take with this equation is you can actually integrate it, and that's just a fancy word for figuring out just kind of how much net effect kind of the whole motion of the spring has, rather than just a single point. And we were able to find out that U, which is equal to the potential energy, which is the energy that's stored in a mechanical system, is equal to 1/2 k, still being a spring constant, x squared, where x is the same displacement. So now we can set up this equation where we've got 1/2 kx squared equal to our 1 joule. Now you'll notice that we have these 2 variables here, and I've kind of drawn this diagram out, but what I can tell you is that when you build your shooting mechanism, if you guys are using springs, then you'll be able to kind of estimate what your x will be to figure out what your k needs to be, and then you just kind of iterate back and forth, bouncing between your k's and x's until you arrive at a combination that works for you. So right now I'll just call it, I think we can just say a displacement of 10 centimeters, so 0.1 meters with 1/2 K, 0.1 meters times 1 joule. So if we multiply that out, we get 1 joule multiplied by 2, which is, so we've got 2, and then we divide by 0.001 meters squared, 0.01 meters squared rather, and our K equals 200, and then our units here are Newton meters, which just tells you the amount of force applied depending on how far you stretch your spring. So a 200 Newton meter spring, that's a pretty strong spring. Maybe you get a couple springs. So if, for instance, you've got 2 springs, then each of them could be 100 Newton meters if you displace them the same amount. Or maybe you have 4, 5, 6. You can have a bunch of springs. For instance, you can even have rubber bands that are very weak, but if you have a ton of them, then they're going to add up and get you a value that you need. So that's basically it for the physics. I'll tell you that I think I did all of my math right. I might have made an arithmetic error a couple of times, but I think everything should be okay. I hope you guys have a fun competition, and remember to always do the math. It really doesn't take all that long. I definitely kind of slowed things down in this video quite a bit, but figuring out these values really helps you make smart engineering decisions at the top, and it saves you money and it saves you time as a team. So it was good talking to you, and this is Dan signing off.
Thanks for watching. If you want more fun content, be sure to subscribe and ring the bell to be notified about our latest videos. Thanks to all of our co-executive producers on Patreon and Tier 2 Plus subscribers on Twitch, keeping fun loud, live, and independent. Thanks to Robotics and GoBuilda for supplying components and providing on-stream giveaways.